Welcome to the course UVC001. In this module, we will discuss about the application of Zener diode as a shunt regulator. So, in the previous module, we have discussed the case when input voltage and load resistance both are fixed. Now, considering a case when Vin is fixed but load resistance RL is variable. So I'm considering a case where my supply is fixed, but my load resistance is not fixed, it is variable, and I have to ensure that the voltage across the variable load should be fixed. Okay. So my input voltage is V in, and I'm marking over here a variable term. So this is indicating that my load resistance is variable. Series resistance R, VZ is given, and I'm saying that PZM is also given. Okay, so this is my node A. You can check as the value of load resistance. I'm mentioning RL, but rather than RL, there will be a range RL min to RL max. So I have to find the range of that particular resistance to which the value of voltage will be constant. So as the load resistance is variable, in order to ensure the voltage constant, the corresponding value of current will also be variable. So it is IL max to IL min. Okay, and I have to find this voltage VL, load voltage. Suppose current flowing through this resistance is I, and current flowing to this Zener diode is IZ. So let me draw one more thing, a graph by which you can better understand the goal over here. So this is my output voltage VL in terms of volts, and I'm writing over here value of RL in ohms. So this is my goal. I want to find the range of load resistance RL, where this is the value of RL min and this is the value of RL max, so that my output voltage should be equals to Vz. That means I want to ensure in this particular range, when my RL is lying between RL min to RL max, I will ensure that the output voltage will be fixed and this will be equal to Vz. VL will be equals to Vz. So I have to ensure this thing. Ohm's law, V equals to simply I into R. So if I am interested to find the value of I, it is simply V divided by R. Interesting outcome is V is fixed over here. V is fixed. So if V is fixed and my R is variable, I will also be variable, and both are having the inverse relationship. Means I over here is inversely proportional to R. So if I am dealing with R minimum, that means corresponding to this R minimum, I will have the value of current IL max. This is the important part which we have to understand here. I'm doing one assumption that RL min, this should be the minimum value of load resistance, which ensures that my Zener diode is working in the breakdown region. It is ensuring that my Zener diode is on. Okay, so means this Zener diode will be replaced by a battery. Okay, so I am input supply V in, R current flowing through here is I, we have already taken. This is node A, voltage VZ, and where PZM is also given. This should be current IZ, as this resistance was my variable resistance, I am willing to find this value VL. So if it is ensured that my VZ is on, so until unless it is on, my output voltage VL should be equals to VZ, and this assumption I have already taken, that RL min RL min is the minimum value of load resistance which ensures that my Zener diode is on. Okay, so I can calculate the value of IL max, and IL max will be simply VZ divided by RL min. This is IL max is VZ divided by RL min. Okay, and you can check here, value of V in is fixed. At this node, value of Vz is fixed. That means the resistance, the voltage across this resistance R is fixed, as the potential difference is fixed, resistance is fixed. So current flowing through this resistance will also be fixed. Okay, so I'm calculating, that is my VR will be equals to Vin minus Vz. Therefore, current I will be equals to simply Vin minus Vz divided by resistance R. Also, if you can recall the term, if you apply KCL over here, what I will receive? I will receive I equals to IZ, I equals to current, I equals to current IZ plus current IL. And this is also very interesting term. You can check this quantity I is fixed. We have just calculated. This IL is variable. So it's a simple mathematics. Left hand side quantity is fixed. Right hand side quantity, one component is variable. So the second component will also be variable. Interesting part is, if I am talking about the minimum value of IL, IZ should be maximum in order to have a fixed value. Both cannot be a maximum or minimum value simultaneously because my I is fixed. So you can check, I have calculated the maximum value of IL. If somehow I will be in a position to have the value of this IL min, so I can get the value of RL max, and that is my objective. Okay, so from this relationship I can easily calculate the value of IL min, and I'm writing over here, therefore my current IL min will be equals to current I minus IZ max. And you can see that IZ max can be easily calculated, this PZM, because we know that IZ max will be equals to PZM divided by VZ, and these quantities have been given. So once I have calculated the value of IL min, I can easily calculate the value of RL max, and now my RL max is VZ divided by IL min. So this is a very interesting outcome. I have already shown you this graph. Now you can check. We have started with the assumption of this, and by this we have calculated the RL max. So this range is calculated. So for this entire range, for the minimal value and maximal value in this range, I will have a constant voltage across the output, which is VL will be equals to VZ. So this is the case when my load resistance is variable. If Vin is variable and RL is fixed. So let us discuss this case. Vin is variable. Okay, this V in is variable. R, VZ, PZM is given. This load resistance is fixed now. And marking now this current flowing through load resistance will also be fixed, IL. Suppose this is my node A, current flowing through over here is IZ, and now you can check current I. In fact, this current will also not be fixed because my input is variable. Load voltage VL. I want to design some this kind of thing. My V in input voltage in terms of volts, I will have V in min to this value V in max, so that in this particular range I will have output voltage fixed and this voltage is Vz. So ultimate goal is to find the range of input voltage which is lying from V in min to V in max, such that my output voltage, load voltage VL, will be equals to Vz. So this is the goal of this exercise. I have to find this range of input voltage in which my output voltage is fixed and which is equals to Vz. So first thing which you have to learn, I have to ensure that in this range my Zener diode should be on. Which reading? I'm assuming that V in min be the minimum input voltage, which is ensuring that my Zener diode is working in breakdown region. My Zener diode is on. So if this condition satisfies, then we can calculate we have to find the maximum value of this input voltage. Variable input V in, resistance R, here it is VZ, PZM is also given, my node A, load resistance RL, VL. You can see that in parallel combination both are equal. Current flowing through here is IL, this current is IZ, and this current is I. So first thing you can check my output voltage in this situation VL will be equals to VZ. So I'm writing over here VL will be equals to VZ, and this should be now taking the minimum value. So it is V in min multiplied by the load resistance RL divided by RL plus resistance R. V in min, this should be equals to RL plus R multiplied by VZ divided by RL. So V in min I have calculated. Now I have to calculate the value of V in max. That is my goal. So now VL equals to VZ. Therefore, current IL will be equals to simply VZ divided by RL. I have calculated this. And now if you are applying KCL at A, if you are applying KCL at node A, then what you will have, current I will be equals to current IZ plus current IL. An interesting point here is this quantity is fixed, this I is variable, and this Z is also variable, IZ is also variable. But interesting part over here is uh, as this is fixed, so if Iz is maximum, so corresponding value of I will also be maximum. So if Iz max, then corresponding value of I will have I max. I am writing it. And you can check if maximum current flowing through over here is, I can easily calculate this maximum value of input voltage. So I am writing from this equation, that is my I max equals to simply IZ max plus IL. For the calculation of Iz max, it is same as we have calculated in previous term. From PZM, I can easily calculate IZM, so I am not rewriting. Okay. Now, what is the value of V in max? What is V in max? So you can check. It is drop across this resistance plus this Vz. So now it is I max into R plus Vz, and our job is completed. You can check. We have calculated this. We have started with this V in min. We have calculated this value. That means now range is available. And for this range, we have already ensured that my output voltage VL will be equals to Vz. Okay. So determine VL, VR, IZ, and PZ part A. Load resistance RL is given as 1.2 kilo ohm, 3 kilo ohm, and remaining data is given in the circuit diagram. This value is given as 16 volt. This resistance is given as 1 kilo ohm. VZ is given as 10 volt. PZM is given as 30 milliwatt, and load resistance RL is given. Different values of load resistance have been given. Okay, so let's see the solution. And you can see that we can start with the process. So temporarily remove this Zener diode. So I'm redrawing the circuit. 16 volt, 1 kilo ohm, 1.2 kilo ohm. Zener is removed, and as per our practice, taking voltage this V dash, and in fact I am writing the current I. This current is IL, and this current is IZ. Okay, so what is the value of this V dash? V dash will be equals to voltage across 1.2 kilo ohm resistance. Okay, so we can apply voltage division rule. 16 multiplied by 1.2 into 10 raised to power 3 divided by 1 into 10 raised to power 3 plus 1.2 into 10 raised to power 3. So one can simplify it as 16 multiplied by 1.2 divided by 2.2, and V dash 8.73. My V dash is less than Vz because Vz was given as 10 volt. This was given as 10 volt. So this indicates that Zener diode is off. My Zener diode is off in this case. And this is my part A. In fact, we are talking about the part A. So as it is off, that means it is working in reverse bias mode of operation. And you can see that if it is off, that means Iz equals to 0. If Iz equals to 0, that means Pz will also be 0 watt, because it is Iz into Vz. What about VL? Voltage across load resistance. VL will be now V dash, which is 8.73 volts, and I can easily calculate the value of VR, that is voltage across here. So my VR is simply 16 minus 8.73, so 7.27 volts. So I will be equals to IL equals to 7.27 milliampere. Now let's proceed to the second part. See the effect if I am increasing the load resistance from 1.2 kilo ohm to 3 kilo ohm. Okay. I am now drawing the circuit for the case when Zener diode is temporarily removed. 1 kilo ohm, V dash, 16 volt. Now it is 3 kilo ohm. Okay. So calculate V dash. Now it is 16 multiplied by 3 into 10 raised to power 3 divided by 1 into 10 raised to power 3 plus 3 into 10 raised to power 3. It is simply 16 into 3 divided by 4. So it is 12 volt. And interesting part is this, now my V dash, which is equals to 12 volt, is greater than Vz, which is equals to 10 volt. So this indicates that my Zener diode is on. My Zener is on. So if Zener is on, let me draw the circuit diagram again by including this condition. 16 volt, 1 kilo ohm, node A, current flowing over here is I, this current is IZ. Now this will be 10 volt. V dash is required for the testing purpose only, for the comparison purpose. Once Zener is on, it will replace by a battery of Zener voltage. And it was 3 kilo ohm. Current flowing here is IL and voltage over here is VL. So outcome is, as Zener diode is on, therefore VL will be equals to VZ, and now it is equals to 10 volts. So first thing is calculate IL first. IL will be VL divided by RL, and now it is 10 divided by 3 into 10 raised to power 3. So it is 3.33 milliamperes. That is my IL. Now next, calculate the value of VR. So VR is simply V in minus VZ, and it is 16 minus 10. So it is of 10. So 16 minus 10, that is 6 volt. VR will be 6 volt. Now I can also calculate the flow of this current I, and this current I will be VR divided by simply R. So it is 6 divided by 1 into 10 raised to power 3. That means this is my 6 milliampere. And now I have to calculate the value of IZ. So my IZ will be equals to simply I minus IL. This I have calculated from KCL at node A. I have directly written, and this value is 6 milliampere minus 3.33 milliampere. So this value becomes 2.67 milliampere. Now calculate PZ. So PZ will be equals to VZ into IZ, that is 10 multiplied by 2.67. So it is 26.7 milliwatt. And now you can check my PZ is less than PZM. PZM was given in the problem. PZM was given 30 milliwatt. So my PZ is less than PZM. That means my circuit is perfect. My Zener diode is still alive. Example 2. Okay, so the example 2 is determine the range of RL and IL for this circuit, where VZ is given as 10 volt, IZ max is given as 32 milliampere, and this supply is given as 50 volt. So means we have to ensure that the load voltage is 10 volt, which is equivalent to VZ, and we have to determine these ranges of load resistance and load current. So this is our objective. So for the solution, uh, I have to draw the circuit first, okay, so that the idea will be clear by considering the situation that my Zener diode is on, my input supply is given as 50 volt, 1 kilo ohm. This is a variable, okay. So over here I will have a variable current. I'm not showing. This current is I, this current is IZ. Suppose this is my node A, voltage 10 volt given. That means voltage across this VL will be equals to 10 volt now, and value of IZM is given. This is 32 milliampere. Okay, so let us first calculate the value of RL min. Similar to the practice as we have discussed in the theory, RL min be the minimum value of load resistance which ensure that my Zener diode is on. Okay, so we can divide it from voltage division rule. That is, my VL will be equals to VZ, which is nothing but 10 volts, and this will be equals to 50 multiplied by this load resistance, and this load resistance is RL min divided by 1 into 10 raised to power 3 plus RL min. Now we have to solve it. It will be 10 into 10 raised to power 3 plus uh, 10 into RL min will be equals to 50 into RL min. Therefore, RL min will be, so it will be 10 into 10 raised to power 3 divided by 40. Therefore, my RL min will be equals to 250 ohm. So if RL min is 250, therefore current IL max will be equals to VL divided by RL min, which is equals to 10 divided by 250, and this will come up 40 milliampere. Now calculate the value of current flowing through series resistance R, that is my current I, and this current I is V in minus Vz divided by R. So this is my 50 minus 10 divided by 1 into 10 raised to power 3. So it is 40 milliampere. And applying KCL at node A, so I will have IL min, and which will be equals to I minus IZ max. And this quantity is 40 minus 32, that means 8 milliampere. So IL min is 8 milliampere. Therefore, I can calculate. Therefore, I can calculate RL max, and this RL max is now VL divided by IL min. So it is 10 divided by 8 into 10 raised to power minus 3, and this is 1.25 kilo ohm. So I'm having a range. My load resistance RL should be lying from 250 ohm to 1250 ohm. This is the one answer. And my second answer is current IL. This should be lying from minimal value which we have calculated 8 milliampere to 40 milliampere. So it is 8 milliampere to 40 milliampere. So ultimately my outcome is, if my load resistance is varying from 250 ohm to 1250 ohm, I will have a constant voltage of 10 volt across the output, and at the same time I will have a range of current is from 8 milliampere to 40 milliampere. So this is a very interesting example. So in example 3, we have to determine the range of input voltage V in so that the Zener diode is on. and remaining database is given in the circuit diagram. We have to determine this V in min to V in max so that I can achieve the output voltage which will be equivalent to this Zener diode voltage. And the database is given. This resistance is given as 220 ohm. VZ is given as 20 volt. IZM. This is given as 60 milliampere. Load resistance is given as 1.2 kilo ohm. So again, we are taking the assumption let V in min makes Zener on. And let me draw this circuit also, which is ensuring that Zener is on, and in that Zener will be replaced by a battery of value equivalent to Zener potential. So this is maximum. I am writing from V in min as I have to start with this 220 ohm, 1.2 kilo ohm. Interesting part here is VL will be equals to VZ, and that is equals to 20 volts, as this is 20 volt given. IZM is given as 60 milliampere. Again I am marking this as node A. Load current IL is fixed now. VL will be equals to VZ equals to 20 volt. This will be equals to V in min multiplied by 1.2 into 10 raised to power 3 divided by 1.2 into 10 raised to power 3 plus 2 to 0. So let me write V in min will be equals to 20 multiplied by 1420 divided by 1200, and V in min will be 23.67. So this quantity is 23.67 volts. So this we have calculated. Now let us calculate the value of IL. IL equals to VL divided by RL, and it is my 20 divided by 1.2 into 10 raised to power 3. So it is my 16.67 milliampere, and the value of current I, in fact this particular current I, and this is my current IZ. So current I will be equals to current IZ plus current IL. This quantity is fixed. So corresponding to IZ max, I will have current I max. I have to calculate V in max, so I need IM max. So my IM will be equals to now here 60 plus 16.67, that is 76.67 milliampere. This is my I max, maximum current flowing here. Therefore, V in max will be equals to voltage drop across this plus this Vz. So it is 220 multiplied by 76.67 into 10 raised to power minus 3 plus 20. Okay, and this will come up 36.87 volts. So now I have calculated the range, so I'm just putting the value. So my V in should be from 23.67 volts to 36.87 volts. Within this range, I will have a constant voltage of output. VL will be equals to 20 volts with other specified database. Okay, so I'm stopping this session here. Thank you.